Philip and Thomas will give a joint presentation about session types for Rust.
Well, thank you. I'm Philip, and this is Thomas. And together with Ken, who's down here, we've done this project as part of our master thesis, me and Thomas's master thesis. And it's about session types in Rust. So what are we going to do? Well, first of all, this presentation is about session types in Rust. And the motivation is that we want to develop some safe internal communication protocols. We want to be able to check that two processes or a number of processes that are communicating actually communicate according to a specified protocol. And we want to be able to check this at compile time. So in this presentation, we're first going to do a very short introduction to Rust, just because some people in here might not know it. I know Turan Aaron has just given a presentation next door about Rust just before, but it'll be short, I promise. And then a short introduction to session types. And then we're going to talk about how we've implemented session types in Rust. So, and the motivation for the project is that is this new browser engine by Mozilla called Server, which is trying to solve some of the problems that current browser engines have, which is that they're sort of architecturally dated. Most of them originate from like pre-2000, which means that they don't really take advantage of all the parallelism that current computers have. So Mozilla is trying to develop this new browser engine that tries to do a lot of things in a different way that current browser engines do. So, but one of the problems is that they have a lot of parallel processes that are communicating, and they're communicating across these message-based typed channels in Rust. And that works, sort of, but it leads to some problems with the communication protocols. For example, you might have a sort of a resource handler or something, which takes requests for cached resources. But it also has, there's also a message from sort of a managing process which tells it to shut down. And the way it's implemented right now is that it just has like one channel, which with this big enum of different things that you can do with the process, and that means that both the processes that just want to access cached content and the managing process that can close the process, managing process that can close this file this cache process, they can all send the exit message, and that leads to communication errors, or can lead to communication errors. So there are some sort of implied assumptions about how the communication between these processes is done, and the problem is that the types of these channels don't really enforce these implicit protocols. So, and we're trying to solve that. So, so first of all, what is Rust? Rust is this new systems programming language that is developed primarily by Mozilla, but also by a large community around the language. Some of the most important features is that it tries to do efficient code that is comparable to C or C++ in execution speed. And then it has memory safety. There's a lot of emphasis on concurrency. So it tries to make it easy to do concurrency without data races. It also has a lot of, even though it actually looks sort of like C or C++ or Java, it has a lot of language level, high-level language features from Haskell, like pattern matching and abstract data types, type inference, and so on, which is really nice to work with. But one thing that it also has, which is kind of different from a lot of other current programming languages, is these affine types. So I'm just going to quickly go through what affine types in Rust are and how they work. So just a reminder, we have linear types and affine types. Linear types are where you can guarantee that a value is used at, exactly once. And there are something called affine types where you can guarantee that a value is used at most once. So Rust only has these affine types, which is very important for later. Just keep that in mind. But what it does is that if we have an affine type foo and some consuming function do something, we can instantiate a value of type foo and then actually call this do something function with the value. And then this call will consume the x, take ownership of the x, and we won't be able to use the x at any later point in this function. So how does that work? Well, this would be an error, for example, because we've already consumed x here. So the compiler at compile time would actually notify you that this is illegal. Okay. Sometimes this isn't really, well, you want to express something where you can actually use the same value more than once. So for that we have borrowing and references. So what we have here is that if x is an affine type, then you can take an immutable reference to x with this ampersand, and you can take a mutable reference to x with the ampersand mut. And that allows you to actually use x twice down here, because you make a reference to x, and you pass that to this borrowing function, do something else. And then you can actually, well, I forgot to put that in here, but you could actually have another call down here that do something else. So that's helpful. Okay, so what is session types and why do we want to use them? So this example is an ATM. Imagine that you're going to the ATM and there are a number of different things that you can do with an ATM, but the two primary ones is maybe that you want to withdraw money and you want to deposit money. And in order to do that, you might have to log in first with your card or some kind of credentials. So this can be expressed using session types. This is the session type DSL as originally described in a paper from '94 or something. And what it says is that, okay, first so this is from the ATM's point of view. So the ATM will first receive some sort of identification, and then it either the credentials are okay, and then we go to this ATM brand, or the credentials are invalid, and you just close the protocol with this epsilon. And then once you've verified the credentials, you have these options for either depositing money and then returning the new balance, or withdrawing money and then getting an okay if there was enough sufficient funds on the account, or an error if there are insufficient funds. So these are the kind of things that you can express using session types. And yeah, so we've tried to model this in Rust, and we do that using these type constructs. So we have from before, we have the epsilon, which is the empty protocol, which means that the communication session has ended. And that's just the X. Then we have the send up here, which is send something of type alpha and then continue with protocol P. And that's, you have the corresponding Rust type over there. You have the receive, you have active and passive selection. So as we saw before on the previous slide, the ATM actually chooses whether or not the credentials here are valid. So this is an active selection. But then it's up to the user, the client, to actually choose whether or not he or she wants to deposit or withdraw money. So this is a passive selection. And we call those choose and offer. And then in order to be able to express sort of recursion or be able to do the same thing more than once, we have these recursion things here. So in traditional session type literature, this is done via this mu and then T and a protocol P, where T might occur somewhere inside P. And then once T occurs, you replace it with P, so you request. In Rust, we do this kind of differently using this rec thing here, which enters a recursive scope. And then in the type sort of later on in the protocol, you'll have these var with an n, where n is these numbers. So that might be a 0 for the closest recursive scope, or 1 or 2, and those are sort of encoded using De Bruijn indices. And then we have this very important aspect down here of duality, which is used to represent the idea that two processes can only communicate if their protocols are compatible, if they are dual. So, for example, if this ATM server expects to receive, an amount of money, then the client must have a protocol where at the same time he is trying to send money, right? So this is kind of intuitive. So the dual of a send A with the next protocol B is receive an A and then continue with P prime, where P is the dual of P prime is the dual of P. So that's how session types work. And now Thomas is going to talk a little bit about how we're going to do this in Rust.
Yeah. So far we've seen how session types are represented in Rust, and we've got an idea of how protocols are specified. But what we need to see is how do we actually interact with them, because we can represent a protocol now, but how do we actually work with it? And that's what I want to get into a bit. But it's a pretty direct translation from the session types DSL to our Rust types. But you'll notice that the sequencing of operation is implicit in all the constructors here. So once I've received something and identify here, the next step is embedded here, right? So you'll have quite a lot of nesting, like at the end. You'll see a lot of these, and that's kind of how it looks. These type declarations here are opaque types. They don't have any influence at runtime or anything. This is just to make it easy for us to name it, because having this in the type headers is a bit much. To the dual, from the client's point of view, we have the protocol. Intuitively, you can take a protocol and just exchange send and receive and choose an offer, and then you have the dual. You can then define it inductively as well, but that's basically what it is. So you'll see EPS is its own dual. And all they receive here, the client sends the ID. And even though the client might know that my ID is okay, he still has to take care of the case that the ATM might actually say, no, it's not okay. So he has an offer here, and then he can go on afterwards. And to program with this, here's an ATM server. So he receives a channel which has so the channel type is the type that we define, and it has an environment that I'll get into in a bit, or maybe not. And but this is the protocol that you can use with this channel. And then all the constructs that you see are defined as method calls on this channel. And it's very important that it's the next step in the protocol decides completely which interaction you can actually call. So the first step for the ATM is the only thing he can do is receive the client's ID, and we imagine that we have some approved function that decides whether or not he's approved. If not, he selects the second branch where he declines the user, and then all that's left to do is close it, because the only step that's left in the protocol is the EPS, and the only thing we can do with an EPS channel is to close it. Otherwise, and then we can return. Otherwise, we continue, and then now we offer something to the client. And depending on what the client chooses, you can either choose one or the other. We either deposit something or we withdraw something. And if we deposit something, for instance, the next thing we can do is we can receive it, and we have to recapture this, and I'll get into this, why this is like this in a bit. Once we call receive, we shouldn't be able to call receive again, because that would be trying to repeat that step, right? So here C, the channel C, is actually moved out of the scope, and what we're given back the channel with that step removed, and we also receive what we were supposed to receive, like the value that we received on the channel. So we get back a new channell, or an updated channel, so to say, and what we received. And it's similar down here, where we make a selection here. The client sends us an amount to withdraw, and if that's not okay, we decline him. We just select that second branch, and then we close the connection. Otherwise, we adjust it, and then we select the first branch to indicate that withdrawal was okay, and then we close it. I think it would be a bit clearer if I put on the types, but that's how it is. That's the server, and let's look at one client. He decides he just wants to deposit something, and he says, okay, I'm sending you my ID. He has a channel with a client, which is the dual protocol of the ATM. He sends an ID, and then he has to offer the ATM the choice of whether or not is it okay or not. If so, and this is the, I would say, the canonical Rust way of doing this, you match on an enum, and then if it's okay, you just assign it back. If not, well, the only thing I can do here, in this case, the only step that was left was an ep, so we close the channel and then we just return. Otherwise, if I didn't have this here, or did something else, it wouldn't type. There's nothing sensible really I can assign to C at this point. But so if I come down here, if I get down here, everything's okay. I'm logged in, so I can say, okay, I want to select the first branch and send you 100 whatever credits, and then I receive the new balance, and I get that here. I print it, and then I close the channel, because that's all that's left for me to. So there's none of these statements, like none of these method invocations that I can actually switch around, because it wouldn't type, then I wouldn't be respecting the protocol. So once you have the protocol, the program tends to sort of write itself, and you'll be reminded that you have to take this step into account, because that's what the protocol specifies. And that's what we found is quite a strong thing. Question?
What's the statement return do?
The statement return
Yeah.
just returns from the function.
What does it return?
Nothing. It's just return is a void.
Returns unit. So
It
this
returns
function
unit,
is-
yeah.
Is that inconsistent with for the left branch it returns C? Right? And then it
Yeah, but
returns-
it's assigned here, so I continue. The C is assigned here, and I continue. Here I return. Like the function, all in all, returns unit.
Return to the get.
Pardon?
The return isn't from the match.
So is it recursive? Is it recursive?
What?
Is it a recursive? No.
The return is from the function, not the match statement. So the C that is returned on the left branch is just returned from the match statement and assigned to the outer C. But if the right branch is chosen, then you can't return anything, because the server or the ATM machine has decided that your credentials weren't valid. So the only thing left to do is just to close the channel and then return from the function.
So what is the type of the C expression?
The type here is a channel with the client inner, with this one, where the protocol is now. I can choose. So the C you have here is a chan that has this protocol here, the ATM client inner. At that point.
Yep.
Yes?
Does the type system force you to go through the whole protocol?
Pardon?
Does the type system enforce that you handle the whole protocol? Like, what would happen if you forget the close, for example?
I'll get into that. That's a good question. That's difference. That's where the difference between linear types and affine types come in. I'll get to that. So that's how you interact with the channels and with the protocols. So one thing I haven't shown you is, and we haven't talked about so much, is looping. And I'll give a very quick example of this, because I don't think I have that much time left. We have the protocol, now we want to be able to loop. So we like to, okay, once I've logged in, I'd like to maybe deposit a few things and then withdraw a few things. So what I could do is, in the type, I could put this recursive construct in front and just replace my terminations with T, so I could go back and repeat this choice here, or this offer here. And in our Rust version of this protocol, it looks like this, and the var z refers to the innermost rec, which is this one. And that's, the piano number, or De Bruijn index encoding of that. It's not necessarily very pretty, but it works. And but in this case, well, now we end up with the protocol where once we've been okayed, like we can't really return from this protocol. There's no way to actually end it. So now we'll add another branch, so the client can actually select to terminate this communication. And the way we do it here, because we only have binary branches in our encoding, and in the session type system, you have a multi-branching, a multi-way branching, and that's a small difference that we have, because we can't really do lists in the types like that, or arbitrary or variadic lists here. So we've encoded it as just as a different kind of list. And the way that will look once you use it in a program is like we've modified the ATM a bit, so it becomes slightly bigger. The interesting bit is this here. So once we've logged in, or we've been approved, or once the ATM has approved the client, we enter a recursive scope. And now I've actually been nice enough to put on the types. So what happens here in the environment is that you have the ATM inner, which is the current protocol, but now on the stack, like the environment is it's a stack of protocols, which allows us to refer to the protocols that we'd like to repeat. So the only item on this stack is the ATM inner protocol again. And once we get to the end of a branch, say at this point I've deposited an amount and I've received an amount to deposit and I send the updated balance. Now I call 0, because this is the type here, which takes the topmost protocol on the stack and replaces it here. So I basically get this one back. So I can actually assign that, the result of this expression, I can assign that back to C. And in that way I can keep looping in the same protocol. And this is where Rust, I think, really shines, because in the quit branch down here, there's nothing useful. Question?
Previously you called them left and right.
Yeah, I know. Because what you get, you'd have to have a match. You call C match, and then on the right branch, you'd have to call C match again. So you'd have this rightwards drift of match statements. So what we did was we implemented a macro to do this. These labels don't have any semantic meaning. It's just to give you some nice names. So suddenly you can actually write deposit. So I know I can recognize that branch. It's very tightly tied to the structure of your list. So if I would swap the branches in this type here, I would have to reorder them here. So that's just syntactic sugar. And there's another thing I like about Rust is that you can write stuff like this. So it looks nice, but you really have to know what's going on. So, yeah. But in this case, as I was saying, once the client has selected close to terminate our interaction, there's nothing useful for me to assign to C, so I have to break out the loop. And if I don't do this in some way, I'd get a type error again. So as I said before, once you have the type, once you have the protocol, it kind of, the program kind of falls out of that, because you have to respect it. The only I'll get into that, okay. So under the hood, we have implementations, The implementation is this. I want to say if a channel if the next step of a protocol is send, then I have the only method I can call is send, and this is how we actually do this. We implement for a channel of this type, so not a generic protocol here, but a protocol where the first step is a send, and the return of this is a channel where we've taken out the next step, and we've progressed the protocol. And the key thing here is the affine types, that the self parameter here is moved into send. So once I call send, I can't call send again on the same channel because it's moved out of the calling scope. So that's where we ensure that you don't, you have a step in your protocol and you can only execute it once, at most once. But because we have affine types, I can't enforce that you actually call in. So in the case of close, as was your question, when I have a channel with EPS and the only thing I can call is close, I can't enforce that you call close, but if you do call something on it, it's the only thing you can call, right? So that's the difference between affine and linear types. If I had linear types, you couldn't just drop a channel that wasn't closed. Yeah, you'd be forced to complete the protocol. And this is how it works. So for every single construct here, we have corresponding declarations that match exactly on what is the next step of the protocol. So I can't call select one when I have a send, for instance. That just won't type. And the way we hand duality is like this. We have a trait. I've noticed in every single talk so far, we've had a trait has something. Has server API, has whatever. And now we have has dual as well. I'm very happy about that. Which uses another neat little thing in Rust, the associated types. So for I define for every single construct we have in our session types DSL, we have epsilon, it's its own dual, so that's how we write that. If for send, I have some p that is the subsequent step, that should also have a dual, and the dual of send AP is then receive a, but p's with p's dual. Yes, question? It's another good question. It's for reasons of safety. Did that answer your question? No, it's because we want, because the traits are public. We can't prevent users from implementing the trait. So we could certainly have users declare another struct and then implement that. Certainly it also has a dual, but then suddenly you could run into, once you're running your program, that you violate the protocol. Using unsafe means that, well, you can certainly still do this, but you have to write unsafe. So we can't.
It's a way of saying it's unsafe for you to implement this.
You really have to know what you're doing.
So it's only the library which should implement this.
Yeah, but there's no way in Rust to have a public trait that you can't implement. And it's exported in some of the functions that we have, so we can't have it internally in the library either. So that's a trade-off, but it's kind of, as I see it, kind of idiomatic Rust that you do have unsafe things, and you can clearly mark what is safe to do and what's not safe to do. So that was we felt that this was okay, that if.
No, this is it.
Yeah.
So I mean, you could have read sealed or closed or something like this, but rather here it is. It's unsafe for you to unseal it.
Yeah. But you could, if you wanted to extend the protocols that you have available, you could certainly do that. But we can't guarantee that. The question is that we would like to guarantee that if you do run it with a protocol, that you don't crash because of a protocol error, that you're not respecting the protocol. So if you suddenly start implementing your own protocol, then we can't. That guarantee that we want to provide is suddenly gone. So what we do is we force you to write unsafe. So we can say, well, in safe Rust, it's safe. In safe Rust, you won't run into protocol violations. Then, so if you write unsafe, well, it's your own. You have the foot gun, for sure, but it's labeled unsafe, right? So, and that's kind of the end for me. There's a lot of different things that we haven't talked about. We wanted to talk about protocols and how we actually do this in Rust. I think the neat thing is that we've actually, it's a library in standard Rust. We don't use any particularly fancy tricks, I don't think. We've considered in the way we've done like performance overheads, because we have binary branching. That's like the major concern for overhead that we've seen. So if I have a long list of options, if I want to select the last ones, I have to navigate through the preliminary choices first to select the last one, right? And we've implemented a lot of examples from the literature, and it works quite well. Some of the stuff that we really like in our master thesis are these two things. So we've actually taken Servo and we've used our library to replace some of the communication schemes in Servo among the processes, and we actually discovered like some fairly subtle concurrency bugs through that, where you had some corner cases that you wouldn't normally get into, but suddenly we couldn't type it suddenly. And we also had like another impact was that we had to rewrite some of the code so you wouldn't be cloning a lot of data, because the channels here, like you can't clone these channels. I can't take, because channels in Rust and our channels as well are represented by their two endpoints. But the unidirectional in Rust, you have a sender and a receiver. You can clone the senders, so you can give the sender away to anyone, so they can send to the same guy. But in our case, we can't share any of the endpoints in a safe way, at least so far. So we've had to place some restrictions on some of the cases where the senders were cloned among a lot of threads. We suddenly had to devise a different strategy for how would you actually have multiple communicating threads to a single process, right? They would have to have each their own channel, and then the receiving process would have to have a list of channels or something like that. So we had to rewrite other parts of those. It was not just replacing like a drop-in replacement for channels, that we had to do some extra things to make it work, which is interesting, because then you figure out what is the architecture of the thing, like how are the concurrent processes actually orchestrated, and suddenly you see, oh, why does this thread over here has a sender, because he's not actually communicating with him, right? So there's lots of interesting things. We also tried to get into as I mentioned, the linear types, because we can't enforce that you run the protocol to completion. Once you have a channel, we can't enforce that it's run to completion. And we've tried to write a compiler plugin, Philip's mostly been doing that, that tries to enforce linearity. But this would be a case, this is a good case for actually putting linearity in the Rust language, because it's hard to implement as a plugin. And well, if you're really interested, then I'd say read the paper. And yeah, that's our conclusion. And I don't know if I have that much time left. But we kind of started on the discussion already, so I'll reserve a bit of time for this. No, that's basically all I said, actually. We'll have Ernst Ron coming.
So just give the floor to Aaron, so that
Yeah.
we can start off the discussion. We've had plenty of questions already.
Yeah, exactly.
Cool. Hey, I'm Aaron Turan. I'm on the Rust team at Mozilla. So first of all, this is great work. I think a couple of things. This fits very well into sort of Rust's take on concurrency, which is basically to have a core system of ownership and borrowing, which was explained in this talk, and then apply that in libraries to sort of make various patterns of concurrency more safe, rather than trying to build anything into the language. So I'm really excited that the session type story seems to have worked out so well. So actually one thing I wanted to ask about that, in the examples you showed, right, you had a fairly substantial protocol, like once you had gotten up to the recursive level, but you didn't seem to need any type annotations in the actual implementation. So first of all, that's amazing. And I'm wondering, you said that you had also implemented a lot of examples from the literature. Did anything end up requiring type annotations, or did it always work out this way?
So you need the type annotations in the function declarations,
Okay.
where you declare the channel, what type it has, but then you usually use a type alias to just give it a name.
Right.
And yeah, you need to write the protocol first of all. Right?
Sure.
It's hairy type, but once you've written that, you don't really need to refer to any intermediate protocol steps as such in
Okay, yeah, that's great. Yeah, I mean, so it's been interesting in Rust. There's often a temptation because of the powerful type system to employ it and try to capture various safety properties. Like for example, another traditional example of using affine types like this is the Berkeley sockets API, which has, you can think of it as like a sort of sequence of states where at certain states you're only allowed to make certain calls into the API, and you might be tempted to model that using a sort of similar approach. In the end, we've ended up backing off of that kind of thing a lot of the time, just because the kinds of bugs you would be capturing there, A, don't arise that often in practice, and B, if you ran the program at all, you would find them, basically. They're very easy to catch. But I think, it sounds like session types, the trade-off may be a little different. So I was wondering, could you elaborate a little more on the sort of subtle bugs you were mentioning in Servo that you were actually able to catch? And did this actually land in Servo? Is this being used?
It's not landed, to answer the last question. I wanted to talk to last time once he gets in, because I don't know how interested he is in that. I don't really have an impression of that. It's difficult to give a short description of the types of bugs, but it's mostly that someone expects to be sent a message that suddenly doesn't arrive, or two messages are sent by two, because you have the shutdown sequence is tricky in Servo, because you have different modes of shutdown. You might just want to shut down a single pipeline, you want to shut down the entire application. And defining who is actually shutting down which processes it's implicitly understood who is responsible for who. And what we found is that in some case, there was a single case where that responsibility wasn't handled by either of the processes that could have taken that responsibility.
Mm-hmm.
And so it was just dropped on the floor. But still one process expected to receive an acknowledgement, okay, I'm actually shutting down, and that just never occurred. He was trying to receive on the channel and suddenly dropped. It was a tricky corner case, I thought. But they arise.
Right.
I don't know how, because it was a corner. It's not a corner of Servo, but it's not the entire Servo application either. It was one particular, I think 3 or 4 processes that we then said, okay, we'll replace it here and see how it works. So we haven't actually done it for the entire Servo code base. And that's the next thing that we'd like to see. If we do it, could we actually do it for the entire Servo code base?
Right.
That would be the next step.
Right. Cool. So another question in terms of usability, if you do make a mistake and try to send the wrong kind of message, what kind of error message do you get out of the compiler? Is it readable at all?
A big one.
Yeah. Okay. That's what I was afraid of.
One of the features that we've been talking about would be nice if because we have the names, we have the type aliases. Yeah. If it knows that this big type actually has a type alias, write the type alias instead of the expanded type. Because it does give you the entire type.
Yes, I see.
It can be very big and heavy.
Yeah.
Videos are not nice.
But it's kind of, after a while, you get the Stockholm syndrome, and okay, it spits out this error message, and I need to look kind of here to figure out what we're going. But it's usually something like this big channel with all this big type doesn't implement the method send.
Mm-hmm.
Then you have to find out, okay, what was the struct actually? What was the type actually there?
Yeah.
At that point.
Yeah. Okay.
But I haven't found cases where it was incorrect. It's usually like, okay, I forgot this step in the protocol. That's usually what it signifies.
Right. Okay, then I had just a couple sort of smaller detailed points. So one regarding sort of linearity versus affinity. So one pattern that we sometimes use that might be helpful is sort of dynamic linearity checking. And so what I mean by that is if you have some value you don't want to be dropped on the floor, well, you can write a destructor for that value for when it's dropped and use what we call a destructor bomb that basically okay, if this ever runs, then, panic. And then something like close basically diffuses the bomb. So that might be sort of one way to get at this where at least you would get some indication.
Unfortunately, it's not, I think, at the moment possible because
Yes.
So that's the problem. They're all channels with, so they're nested types, sort of, and we can't specialize them.
Yeah. So specialization, I actually have an RFC for specialization, so maybe that'll help.
I did the test though. I just embedded a Boolean type in the channel. Once you call close, you just switch that and test that in the destructor.
I see.
That's the hacky way.
Yeah, right. Since there's sort of only one way to finish a channel, that makes sense.
Yeah.
Sorry, so one last point I wanted to make in terms of the performance overhead. So you didn't talk very much about the implementation. But one thing that's emphasized a lot in Rust is tight control over memory layout and being able to avoid extra allocations and indirections. And the channel implementation here, basically because you're passing things of all different kinds of types described by the protocol, you need a uniform representation, and you do that by boxing. So you basically have an extra allocation and indirection, which might be a reason not to use this framework, right, if you're very performance sensitive. So I wondered if you thought about a different implementation scheme where you actually had multiple channels that could primitively send the different types that you're going to encounter in a protocol, and basically as you get to a different state in the protocol, you use the appropriately typed channel, but that way you avoid sort of the boxing.
That's a good suggestion. We've actually talked a little bit with Manish, who's also a Rust and Server contributor, about ways of improving the sentence and story. But that's definitely one possibility. And we actually looked at like analyzing, because you can sort of do compile time analysis of the protocols, and then actually sort of specialize your the sender functions and all that sort of stuff.
I see.
So we've looked a little bit into that. Another approach is to have a dynamically sized like queue or something, because right now we're just using the standard channel senders and receivers from Rust. But you could, I guess, sort of roll your own and then have that be dynamically sized.
Yeah. I mean, it's part of the reason I raised this point is I think you said that Servo currently is using an enum for these channels, and that means basically every message you send is the size of the largest variant of the enum. So you might actually be able to get performance gains if you were able to specialize things more, right? So okay, that's all I had prepared. So maybe I don't know how much time we have for other questions.
Let's open the floor for a few more questions. We're running over time, but I don't think lunch is until 12:30, so I don't know. Okay. If you're not interested in the questions, feel free to leave, but otherwise I think just keep the discussion going. Yeah, question now.
So you've been using, when these things for the recursion, Rust does have recursive types. Is there any chance you would deploy Rust recursive types or your recursive? I did not mind.
So right now we're using these different indices, and you're talking about other ways to do this recursion.
I mean, just write in Rust, you can type recursive. So I could just define these type as different recursive. Right?
Yes. Not a type alias. You have to define a first class type. Yeah, I mean, right, so, yeah, I had the same question actually, but I think there are a couple of reasons, there are a couple of things that make this tricky. So you can't do that with type aliases as they're using, right? Right. And also, like, there has to be some point of indirection in a recursive type, or the type checker will sort of not accept it because the type would be infinitely sized. So also, I think you'd have to figure out some better story with the dualization. If you're creating custom types for these recursive things, you'd also have to provide your own dual, right? Your own impl of dual for each, or has dual, I guess.